All right, thank you all. If I wander away from the microphone, you'll let me know. Thank you so much for bearing with me and inviting me here. I couldn't make it last year because of hip replacement, but here I am. So we're going to talk about what the title says, the cosmic circle of life and seeing through the eyes of Einstein. And I'm going to put Webb's discovery in somewhat of a spiritual context. Whenever I talk about distances, I'll use light years, which is of the order of 10 to the 13 kilometers or miles. I'm going to not worry about a factor of 2. And when I say something is 10 billion light years away, like these galaxies, I'll imply that the wideness of the field is like looking at the universe through a tiny straw or stir straw. So the lateral distance will be about 1,000th of the distance you're looking away at. So 10 billion years is 10 million light years across laterally. Okay, we're looking back, one of the first images taken with Webb, at stars in our own galaxies. Just a hint, we avoided that bright one like the past. They're like, you know, bugs on the windshield on your car when you drive through intergalactic space, where the houses and the cities are the distant galaxies. There's only a few stars in our own galaxy. Everything else is distant. Next slide. For some reason, the next button doesn't work, but my friend over here does it for me. So, outline. Pope John Paul and his influence on my life. 2 charts on that. Then the first Webb images on the cosmic circle of life, and viewing the universe through the eyes of Einstein. And then a couple of other spare charts. There's a link to my talk here in case you want to PDF. The next slide shows you Pope John Paul II. I had just arrived at ASU in 1987. In fact, we were praying for him during an earlier conference in May of 1981 when he got shot. And we had a mass in Sicily, where I was at that time, and he recovered. So 6 years later, he is at ASU, gives a mass, 70,000 people. First thing he says, "This is hard for me to be here. This is Sun Devil Stadium." Yeah, great mass. At the same time, he gave Peter Strittmatter, the director of Stewart Observatory, funding to build the Vatican Advanced Technology Telescope on Mount Graham, Arizona. I want to dedicate this talk to him, my hero, as well as Father George Coyne, who is no longer with us, and Jesuits Richard Boyle and Chris Corbally and Guy Conselmagno, who are were operating the Vatican Telescope. So unbeknownst to me, this had inspired my lifelong mission to with Hubble and Webb. The Lord himself will establish a house for you. This was one of the first facilities I used. Next, please. So we were lucky enough almost 10 years later to take the first picture with the Vatican Advanced Technology Telescope, a galaxy seen in near ultraviolet light. This says the beauty of nature in ultraviolet light. We gave the Pope a copy in November '96 when we were visiting the Vatican for a conference. And a month later, I got this Italian thank you note back from the Holy Father. Now, if the fellow that stands in the feet of Simon Peter sends you a letter, that does inspire you, okay? Thank you, John Paul. The next slide, we'll get on with Webb. Launched on Christmas Day, birthday present for Jesus, from Kourou in French Guiana. We had a European-Canadian collaboration, December 3.5 years ago. In the next slide, you see the Webb telescope fully undeployed yet, just 8 minutes after launch over Saudi Arabia and the Horn of Africa here. Next. You will see the first, it took a couple of months to cool down, right? It's an infrared telescope, 6.5 meters across. It's not like Hubble, it's 2.5 times bigger. It works in the cool, it's literally a very cool telescope, but it needed to cool down. So it took its first selfie of all 18 hexagonal mirrors that were made out of beryllium, very lightweight element. And it then took images of a star the first time, assuring that they were in focus. Of course, they were not. It took a while to focus. So the next time, the next slide, shows the stars all in focus, originally all 18, and then folded together in an 18 times brighter image of the same star. Then we knew we had it. This was in March of 22. Everything worked. Next, you will see in, a brighter star that my colleagues at Goddard Space Flight Center, not too far from here, took. That was March 16, 3 years ago. And they were excited about the perfect focus, of course. They were more excited about all the distant galaxies behind this star, because Webb could see a lot of those too. So Webb is looking back in time. Wherever I can, I'll show you the link to the press release. Stay close. Oh, take the mic with me. I didn't know you could do that. You'll have to help me get it out. Oh, okay, like that. Sorry. Thank you. Sorry about that. So the next slide shows the first image of the whole family of cameras, the European near-infrared spectrograph, the U of A near-infrared camera, another European mid-infrared imager, and the Canadian fine guiding sensor that holds the telescope still while it's moving through space and taking a long exposure picture, and a near-infrared spectrograph made by the Canadians. So this is an image of the Large Magellanic Cloud, the companion galaxy about 160,000 light years away. It runs between 1 and 8 microns in wavelength. Next, we will see an enlargement of that. This is the image taken by Webb. This is the image taken 20 years earlier with a much smaller telescope, 80 centimeters, the Spitzer Space Telescope. And you can see how much the resolution has improved. And you can now see the gas and the dust between all these stars in the nearby companion galaxy to our Milky Way. Next, you'll see and I need this as an introduction to the circle of life, the cosmic recycling of elements. The periodic system you learned in high school isn't correct. Not the real one, anyway. It is correct. It lists all the 103 elements. In blue, hydrogen, helium were formed in the Big Bang, a little bit of lithium. In green, you see the ones that were formed in the later stages of stars like the sun, when they throw out their outer layers. We'll get to that. In yellow, you see the elements that were made by supernova explosions. And more recently, we discovered from LIGO neutron star mergers that the purple elements were formed in exactly neutron star mergers, and some are formed in both. This is, however, not the real periodic system. Next, you see the real one. Yeah. Okay, so this is, and I'll explain, if I have time, I'll explain, but it's not the topic, why aliens haven't been here yet, right? So because you need, they have exactly the same periodic system as we are. We have the same chemical elements and physics and chemistry throughout the universe. That is the premise of relativity. So there's 76% hydrogen everywhere, 24% helium in the Big Bang, and then some of that later formed inside stars into what we know as carbon, nitrogen, oxygen, silicon, iron, everything else you had for breakfast, and that makes up our bodies. Yeah, so we were made, as the previous diagram showed, in the interiors of stars from those chemical elements that are now present in these proportions. And so if gold or titanium is rare here, it's rare everywhere in the same proportions. Yeah, same laws of physics apply everywhere. So I couldn't resist showing this in the perspective of Jeremiah 3:22. The Lord established my covenant with day and night and the fixed laws of heaven and earth. That's a deep secret. This periodic system, true everywhere. Next slide, please. So this is now going to the cosmic circle of life, the first image that Webb, or one of the first images Webb took of the Eagle Nebula. This was done with Hubble 25 years earlier, almost 30 years earlier. We've all seen this. It's on a US postage stamp. It's about pillars of gas about a light year across, seen in the background of bright stars, and seen much better in the infrared, where just like a sunset, you poke more easily through the dust and you can see the stars behind and inside these columns. The next slide shows you an enlargement of this in the mid-infrared, same object, light years across. You can see at the end of these fingers, stars like the sun are forming. This is how the sun and many other stars like the sun have formed out of these pillars of gas, in our case, 4.5 billion years ago, yeah? Next slide, please. This shows you the context how that happens. This is now again in the companion galaxy, 160,000 light years away, a bright star cluster seen by Webb, the Tarantula Nebula. And in the next slide, you will see an enlargement by Hubble in the optical ultraviolet. And these stars are very massive, they live fast, and they die young. I call them the cosmic fraternity members. Please don't do this at home. But they serve a purpose, right? Their ultraviolet light shapes this gas and dust. Look at this finger, it looks like my hand. At the end of this finger, in the next slide, in the infrared, you see a star like the Sun forming. This is now an Eagle Nebula in another galaxy. This happens everywhere, yeah? Courtesy of these fraternity members. They live only a few million years. They produce this vast ultraviolet radiation, and they sculpt these columns to form stars like the Sun. Thank you, Lord. Now, next slide, please. So here you see it in full glory with Webb, one of the first images of the Carina Nebula, 7,600 light years away. And the bright stars that do the sculpting are here, and the stars like the Sun are formed in what I call this cosmic beachhead. It's not like sand, it's dust, but it's being sculpted not by water waves, it's being sculpted by the ultraviolet radiation from these stars. By the way, yeah, God has given a name to every star. He made Abraham do it, but I remind you that there's about Avogadro's number worth of stars in the universe, and that is, you know, over the average human history, about a trillion stars to be named by every human. That would be 400 stars per second per human. So, needless to say that Abraham couldn't finish this. The next slide shows this further into the infrared, and you can see also here in this cosmic beachhead, stars like the Sun are forming courtesy of these brighter stars that are off the chart here, that are sculpting this enormous pile of gas and dust. Next, please. You see this even in the Orion Nebula, very nearby. This is only 1,300 light years away. And if you zoom in, you can actually find a protostar forming here that contains a carbon chain called methylcation. It is, you know, CH chain that is not life, but it's a building block of something that could host life maybe someday. Next slide, please. This is how a star like the Sun formed. We call this the Hourglass Nebula. A star about 30% of the Sun's mass is forming in this inner disk. It's spinning sort of horizontally. That becomes the protoplanetary system. In the process, it illuminates this enormous mass of gas and dust, some of which is outflowing in this process. The next slide shows this in a little more detail. How am I doing time-wise? I can't see my own watch here. This is the Rho-Ophiuchi dark cloud, 450 light years away, so you're looking just about half a light year across here. And inside this pile over here, a new star like the Sun is formed. These guys have already just formed, and it's squirting out these jets of gas while the protoplanetary disk is spinning this way. And in about a million years, that will be a shining star with a debris disk that's forming planets. So this is another cradle of star formation. And it contains PAHs, as we call polycyclic aromatic hydrocarbons. Again, it's not life, but it's organic building blocks that someday could form life. So the next slide shows another one, a more dramatic, more massive star that's expelling its material before it's forming. It already started shining. Everything that shines shows this typical, you know, beautiful Christmas tree star feature that's a courtesy of the telescope optics. Star formation is very messy and also pretty inefficient. Not all the gas gets used up. And when stars die, as you'll see in a minute, they do the same thing all over again. So there's a lot of recycling going on, the cosmic circle of life. Keep going, please. Yes, so here's the Southern Ring Nebula. You get to see the northern one in just a minute, 2,500 light years. This is a sun-like star, not actually that one, but the companion, that's expelling its outer layers courtesy of that 24% helium. The 24% comes because the Big Bang was so fast that not all the hydrogen could form helium in the initial thermonuclear fusion. That's because the neutrons that were needed had a decay time of 15 minutes, and therefore only 2,400. Oh, look at that. This suddenly works. I don't know why that is the case. Well, good. How about that? So had 24% helium left after the Big Bang. And that helium, after the hydrogen burns up in the core of a star and then the outer layers, when it becomes a giant, that helium starts flaring up in the inner core of the star. Nuclear fusion build up the heavier elements like carbon, nitrogen, oxygen, everything is in your body. And then eventually happens in the outer layer. And when that happens, the outer layer becomes unstable and the star puffs itself up to about 100 times the size, can swallow up the Earth and Mars. And then the remainder material, which is now the bottom of the periodic system, also gets thrown out. And it is out of that material that new stars and planets can form. Yeah? So the buttons do work. Thank you, my friend. Here's an enlargement. So I couldn't resist Genesis 3, verse 19. For dust thou art, and dust to dust shalt thou return. This is true for stars, it is true for planets, and it's true for people. Yeah? The cosmic circle of life. Here it is in the mid-infrared, same story, but you see the filamentary dust a little bit better. You also see edge-on background galaxies. And because of this process, new stars will form sooner rather than later, with planets, of course. Here's the Northern Ring Nebula, absolutely beautiful, one of the most gorgeous in the near-infrared and mid-infrared. It's that central star that's left over as a white dwarf. Courtesy of that 24% helium, the outer layers get thrown off. This is how the sun will come to an end in 5 billion years. You don't have to sell your real estate yet, but it will happen. Yeah? Okay. More examples of for dust thou art and to dust shalt thou return. This is a massive star, one of these fraternity members, 30 solar masses, lives only 2 million years, and then it will go boom. This is just before it goes boom. It throws out these outer layers courtesy of the helium, and then it will go supernova in a few 100,000 years, or maybe sooner. This is also a big source of the cosmic dust. This must be the old version. I'll skip over this for sake of time. Here's the last cosmic circle of life talk before I get to Einstein's part. This is one you can see with a small telescope, Cassiopeia A, in the Cassiopeia constellation. You can see all the colors indicate various chemical elements, carbon monoxide. There's also water and other CNO components that you saw here in color. The star itself is no longer visible. This is a couple of 1,000 years after it goes boom. So the cosmic circle of life takes gas, cools it down, makes stars and planets, and then the stars cast out the outer layers, which contains new material, including gas and dust, from which new planets can form. So this happens everywhere in the universe. You can see it in the near-infrared in nearby galaxies, where the red is the hydrogen gas, the blue is the hot stars, and in the mid-infrared, where the expelled dust forms these beautiful spiral arms similar to these. It's the same galaxy, but much more fluffy. And it's out of all this material that someday new stars can form. So the same is true as we saw for individual stars, for galaxies. To dust thou art made stars, and dust to dust thou shalt return stars, and dust thou shalt return. So this is true everywhere in the cosmos. Here's an example of 12.5 or so galaxies. They're not all the same, but they all do something similar. They produce new stars from the surrounding gas and dust, and then they cast out that gas and dust when they're done. So the cosmic circle of life rules throughout the universe. All right, then what did Einstein have to say? Well, he predicted many things, all of which he didn't believe at first. The dark energy or cosmological constant, he called his biggest mistake. It wasn't. Gravitational lensing, he predicted against his will. A colleague prompted him. He got it exactly right. That actually gave him the Nobel Prize. Black holes, he thought, were absolutely detestable, but it followed from relativity and then the Hubble expansion. So never say never, Albert, but you did a great job. So we're going to talk about the gravitational bending of light. So one of the images Webb took, this is Stephan's quintet, 40 million light years away. There's 5 galaxies. This one is in foreground. This one is of particular interest. They are merging and colliding, the cosmic fender bender or train wreck that happens a lot early on in the universe. Here you see a mid-infrared image of that. And in the mid-infrared, you can see that the northern galaxy contains this star-like feature. That ain't no star, that is the accretion disk around the supermassive black hole, about 10 to the 8 solar masses. And that's actually fairly common. Yeah, and so we call it the beast, and we will show you how the beast gets fed. Here's a modest galaxy like our own with a beautiful spiral structure, not a great or any black hole visible in the center. The black holes are usually the massive ones in the center anyway. Here's one with a respectable black hole 24 million years ago. And you say, Roger, how can you say a black hole shines so brightly? Well, of course, black holes are so massive that even light cannot escape. The escape velocity is bigger than the speed of light at the Schwarzschild radius. But the immediate area is so dense and so hot, X-ray temperatures 10 to the 8 degrees, and so much material falls in that its brightness is literally visible till the edge of the universe, and we call that a quasar. So when we see that, we know a black hole is inside. Yeah. Here's another more blatant example, 220 million light years away. And this is a supermassive black hole feasting on the infalling gas and dust. And it also spits out in opposite direction to its rotation relativistic jets of material. So these things are very active. They're in fact the most user-unfriendly regions of the universe. We'll get to that. We live in a special place far away from such a beast. Yeah. Here's a this is what some of my students did with Webb, one of the first images, a background elliptical, foreground spiral, just like our own. If this is the center of the galaxy with tiny black hole, we would be here somewhere, but it's not our own galaxy. It's about 100,000 light years across. And we use the regular light distribution of the background elliptical to map the dust in this spiral. And it's the same kind of dust we see in our own galaxy. So again, the cosmic circle of life is true everywhere. When you take an enlargement of this thing, you see that there is this smiley face here at 10 o'clock, enlarged over here with the counter image there, and that's a gravitational lens. There's a galaxy in the background, not at the same distance, just behind here, whose light gets bent via different light paths, so it turns into a stretched image and a counter image. This is a common effect. Einstein predicted it just exactly right. This was the first image revealed by Webb almost exactly 3 years ago by President Biden himself. One of my team members planted the image, the other one analyzed the data, and then we were going to release it on July 12th, but the president wanted to release it a day early, and we wouldn't stop him. There was a big release on that. Fortunately, the president was called away out of the meeting by his national security advisor, so he didn't scoop us on the Nature paper. Important point here, our Earth is 4.5 billion years old, and the sun, as you know. These galaxies are already 9 billion years old back there, 4.5 billion back in time, right? 13.5 billion years old in total. So these galaxies, especially this big monster, is 3 times older than the Earth today. Yeah, we are cosmic late bloomers. This is the Hubble image of the same. So we're not an early galaxy. We're a fairly isolated galaxy, and I'll argue that's a good thing. But we're a cosmic late bloomer. That's also a good thing. Here's some of another galaxy cluster. This contains now of the order of 10 to the 15 stars worth of mass, so it does an enormously good job in bending the light. I used to be able to say that there were about as many stars in this galaxy cluster as there were pennies in the national debt. That's not true anymore. And the cluster hasn't increased its number of stars much. There is a tiny background object, red like a very distant high redshift galaxy, one like these, but it's behind the cluster, and its image appears 3 times. A, B, and C, or 1, 2, and 3. It's actually a double galaxy, a little yellow and a little red one. And it's at a redshift of 10 and a bit, about 400 million years after the beginning. Yeah, one of the most distant galaxies seen through gravitational lensing, 3 different light paths visible here. Here's another one. This one is a redshift 6 that's seen in the first billion years, this telephone number. And the actual galaxy itself, which is inconspicuous, is highly stretched or spaghettified into this arc. And there is a single star along what we call the critical curve or the caustic, which is like a line where the magnification is almost infinite. And this object is magnified 9,000 times. So you would need a telescope about a mile in diameter to see it without the gravitational lensing. But courtesy of the lensing amplification, you can see this star. It's actually a binary star seen in the first billion years. That reminded me of Proverbs 3, verse 6. In all your ways acknowledge the Lord, and he will make your path straight. Of course, that means straight in 4-dimensionally curved space-time. Yeah? But it is straight in that space. Okay, here's another example. Highly spaghettified galaxy, one just like that happened to be behind this cluster, and there's another one here, this spaghetti arc. And this one was probably one of the most spectacular ones, came out in Big Think. This is at a redshift 1.78, about 3 billion years after the beginning, and it contains a supernova right here next to the core of this galaxy, three times image, right here, there, and there. I'll show an enlargement in a minute. 3 independent light paths with different light travel times show this supernova, and it was fading with time. It's a type 1a supernova, the standard candle type, 3.6 billion years after the Big Bang, and it gave us a new measure of the Hubble constant. The error bar is still large, but it's on the high side. You probably heard about the controversy of the Hubble constant, and it's on the high side, consistent with Adam Rees's value in the Hubble tension of 73. The star formation rate in these galaxies is so large, of the order of several hundred solar masses a year, as opposed to our own galaxy that produces less than 1 solar mass a year, that we expect another star to go boom here every year or every other year or so. We are regularly monitoring with Webb, because if we get enough of these, we can make a precise, completely independent measure of the Hubble constant that far back in time. Yeah, I'll skip over this for the sake of time. This is probably one of the most massive clusters, called El Gordo, which is like the fat one, like Laurel and Hardy. And this is the thin one, La Flaca, which is a highly stretched, spaghettified object behind here somewhere. And this is what we call El Anzuelo, or Einstein's fishhook, an ordinary dusty galaxy like one of these that happens to be behind this object, or double galaxy here, that gets highly stretched into a fishhook-looking arc. We had a press release on that 2 years ago. There's an enlargement of El Anzuelo, and I want to point out this press release here. You should read it, from ASU. I gave this talk about 2 years ago, 2.5 years ago, and there was a fellow in the audience, 93 years old, and his name was Werner Salinger, and he had known Einstein personally. He was a Holocaust survivor as a kid, came to Princeton, New Jersey, lived on the same street as Einstein. And while Einstein never saw these images, he predicted them, that Mr. Salinger has seen them. And Einstein played the violin for him and so on. You should read that, it's really interesting. Anyway, this is probably our best image so far. It was above the fold in the science section of the New York Times the week before Christmas 2 years ago. It's again one of these massive clusters with this phone number, MAX 046, and it's 10 to the 15 solar masses, and it highly stretches many of these images behind it. So gravity works. Gravity sucks, black holes, but it also works. It does bend the light. And there's a couple of galaxies here where we see many individual stars flare up, not because they're variable, but because they go across these infinity curves that make them temporarily magnify a lot more than average. This was the Hubble version, 122 hours. This is the Webb version, 22 hours. You can see Webb, of course, is a bigger telescope, but you can also see the enormous contrast in color. Look at these two objects over here. Okay, so now we go back to, and these dusty galaxies are the ones that we've never picked up with Hubble, right? They're just too red and too dusty, but Webb picks them up just fine. Let's see, time-wise. Well, I'm wrapping up. So this is probably our most dramatic, more recent ones on the Abell 370 Dragon cluster. We don't actually show you the cluster, it's off the chart here, but there's this very highly magnified arc. It's actually a spiral galaxy that gets completely stretched along this enormous arc. And in this arc, via various epochs of observation with Webb, we found no less than 44 stars going across this infinity line. And we're now in the business of actually counting individual stars at cosmological distance. You couldn't do this with an ordinary telescope. It's only the gravitational lensing that lets you do it. And so I think this is an appropriate verse for that discovery. Now we see but a poor reflection as in a mirror, but then we shall see face to face, right? So we can actually see face to these stars thanks to God's creation of gravitational lensing. So, wrapping this up. Yes, our place in the cosmos. Here's one that came out not too long ago. Redshift 1, halfway back in the Hubble time, there was a series of very young clusters. Oh, yeah, sorry, thank you for that. Did I turn it off? Yeah, thank you. But that's besides the point. There's this massive cluster here halfway back in time, and it's incredibly messy. I'll show you an enlargement in a minute. And our galaxy is a spiral galaxy like this, but further away from a mess like this. And that's special, as I will argue, or at least important for who we are as a galactic environment where we live. These galaxies, there's many dozens of them, and they're very actively merging and colliding, and every galaxy that has this asterisks in the center, which many of them do, have active black holes, and that's a common thing. These are all unfriendly environments. They're dynamically very unstable, and black holes produce a lot of outflow. So the fact that we live in an isolated spiral far away from this mess, I think, is a gift. You know, the Lord himself will establish a house for you, and I'll bring them back to this place and let them live in safely. I think I'd rather live here than in one of these. So we live in a boring galaxy, you know, a cosmic afterthought, only the last 4.5 billion years out of 13 billion years, far away from the mergers and the supermassive black holes. This is one that came out just last week. I couldn't resist showing you that. There was a full 120 hours, one of the deepest Webb images taken of this Abell cluster. It's only 3.5 billion years back in time, but it really magnifies and spaghettifies many of these background objects. And you can see dozens of galaxies that have this asterisk-like feature in the center, which are the feeding black holes. So I will, I don't know how we're doing time-wise, but I will summarize it as following. One more. Black holes. This is a technical chart. Oh, I'm ahead of time. Good. This chart is a lot more complicated, so since I have time, I'll explain. This is the age of the universe. We're here far off to the right on this chart. The Big Bang is far off to the left. This is the redshift, which is a nonlinear scale that maps onto cosmic time, but just go by this. And these are black holes whose mass we know, measured at redshift 6 or 7 when the universe was 800 or 900 million years old. And this is what we think the growth curves of these black holes are over time. And these are the black holes in purple, their masses that Webb has found and measured the mass of, typically in the range 10 to 6.5, 10 to the 8 solar masses. And these red dots are the ones that you find locally, which are lower mass by a factor of 10, and they happen in more massive galaxies. So this is the galaxy mass where this happens. Our own galaxy is 10 to the 11 almost solar masses. So every galaxy has, 10 to 11, 10 to the 10 solar masses, has a typical central black hole of the order of 300 or 1,000 times less, 10 to the 6.5, which is 3 million, to 10 to the 7.5, which is 30 million solar mass black hole in each galaxy. That's about 300 times more massive. A fairly reasonable rule of thumb to use nearby. And we're far enough away from our own modest black hole, which is only 4 million solar masses, 24,000 light years away. A few people got the Nobel Prize for that a few years ago. But here you see all the early black holes that live in galaxies that are a lot less massive, and the black holes are much more massive. So this results in overweight supermassive black holes compared to their host galaxies, redshifts in this range when the universe was 5 to 9 times smaller. So the first, half to 1.5 billion years. And we can now address the question, who came first, the chicken or the egg? The chicken being the galaxy or the egg being the supermassive black hole. It was most definitely the egg. Yeah. So the supermassive black holes came before the galaxies, and they grew while the galaxies were growing, but they might have even seeded the galaxies. So I'll end then with Psalm 74, verse 20. Have regard for your covenant, because hounds of violence fill the dark places of the land. They do. Black holes, not a pleasant, not a pleasant place to live close to. So we'll summarize like this. We were launched finally after 20 years, 25 years, in December 21. We traced the cosmic circle of life, the evolution of stars and dust over cosmic time, and how dust helps forms exoplanets and the building blocks for lives. And Webb is now observing the epochs of first light, galaxy assembly, supermassive black hole growth in great detail, much through the gravitational lensing, which is of great help. And we're monitoring the formation of the first stars and star clusters and black holes after 200 million years. So we hope to eventually outline the entire history of galaxy formation. The spiritual contact to take away, we have a proper place in the universe. From cosmic dust we were made, and to cosmic dust we shall return. True for stars, planets, and people. And we as a galaxy are late bloomers. As a solar system we certainly are. And we live in a cosmic, quiet place, which is a good thing. Yep, thank you very much. Well, Webb doesn't always run on time, but today we did. That's right, yeah, that's right, yeah.
Thank you. All right, so we have time for about 10 minutes worth of questions.
All right, well, I hope I was provocative.
Thank you. One question regarding, I've seen many, I'm over here in front of you.
Yeah.
I've seen many images of smeared images of galaxies and such because of gravitational lensing. Do we have enough data in these images that we get to actually sort of deconvolve things and either determine the original shape of the object or determine the properties of the object doing the light bending?
Sure, yes, a very good question. We can turn the lights back off. I mean, there's two reasons Hubble and Webb are so good to prelude is. A, they're above the atmosphere, so they don't vibrate, and the image is very sharp. B, and actually far more important, the sky brightness is between 1,000 and 100,000 times brighter than from the ground. And so these images are best appreciated in the dark. Yeah. So yes, we have models, precise models. I'll use this one as an example. Where is the mass that does the lending? I hope I heard your question good enough. So there's 3 galaxies here, a big merging train wreck, and 4 or 5 over here. And we count the stellar mass or the light in total, and we know how much mass each of these subclumps has. There's also this one, that one, and one off the chart. And then we place objects, they're all numbered here, at various distances behind there. And then we do the gravitational ray tracing that tells us where this image ends up. And you see there's an object 1.1b, but there's somewhere else also a 1.1a. And if you place that original galaxy, which is an inconspicuous smudge just like this somewhere behind here, if you place it at the right location, you get exactly the image 1.1b and 1.1a that you predict, assuming you know the distance or redshift. So it's an iterative game of supercomputing and getting the gravitational ray tracing right. And then we know where all the matter, including the dark matter, in these 2 piles ought to be. And that's how we know the total mass and how much lensing it does. Great question. Other questions?
Yeah, I have a question back here.
Yes.
2 questions in a common. Question 1 is you just alluded to a larger computational approaches, and these are huge data sets already, and I'm wondering if you could comment on, with the evolving new computational abilities that we have, what we're going to be able to pull more out of these data sets. Question 1. Question 2 is, This is spectacular. I mean, I wanted to change fields and become a student in what you're doing.
Yeah.
The second question is the Nancy Grace Roman telescope is being built a few miles from here down at the Goddard. And if you could just give us a sense for how many more orders of magnitude of data collection we're going to get from that. And then my comment is I've probably never said this before, but I would actually like to see my taxes increased to pay for this work. So.
Yeah. So yeah, we had, thank you, very good question. We had the same question when I was in Capitol Hill the last few days to plea for the NASA and NSF science budget. And the data streams are in fact enormous. I liken Hubble to, taking a sip from a fire hydrant, with is nothing compared to Webb, which is like akin to taking a sip from the Niagara Falls in terms of data stream. And Roman will be another 100 times bigger. So the data needs to live in the cloud. You can't get it all down to a workstation anymore. And you need supercomputing and very fancy algorithms and AI to deal with it. It's really state-of-the-art. Astronomers always pushing the computer technical AI know-how. And that message, by the way, went over well on both sides of the aisle. Yeah, and I can tell you that behind the screens, no matter how much, crazy things you see go on in the news, behind the screens they're trying to work out a sensible solution. Whether that will happen, we don't know, but it may happen soon. Other questions? Yeah.
I understand the formation of the elements. What do you think? An idea of what will be the John? What will be the fate of the elements after, to a black hole and so on?
Well, when they fall into a black hole, they either end up in singularity or very dense. We don't know. There's just no information because it's behind the Schwarzschild radius. There's many theories on this. Some people say that the mass is there and the mass remains there. Black hole weighs something and it spins and it even has an electrical charge. But the elements themselves may heat up to infinite heat and start fusing again or whatever they do inside the Schwarzschild radius. Yeah, they do not disappear from the universe, but we can't see them anymore. Great question. Other questions? Yes, please.
I saw one slide that had a boundary to infinity. Could you comment on the edge of the universe?
Yeah, there is no edge in space. It's infinitely large. However, there's an edge in time, and that's the Big Bang itself, which is 13.8 billion years ago. And so the amount of universe we can see has a radius of 13.8 billion light years. Yeah, and so you can consider that the effect, we call it the Hubble radius. It's not a physical edge in space. It's only the part we can see. So the actual universe can be way bigger. It would presumably still follow the same laws of physics if everything is consistent. Good question. But there too we're speculating. Any other questions?
For the correction, the diameter of the universe is 96 billion light years because of expansion.
Yeah, the age, it depends on whether you use the geometric distance or the proper distance or the luminosity distance. There's 3 different versions, but yeah. When you take the expansion into account, it's actually bigger. I wasn't going to get into that. A question over there.
Hi, yes. I'm interested in the Hubble tension. This is the only case that you have where you're seeing repeatedly these magnified supernova type 1a, or are we getting lucky and do we have similar instances?
Well, Reese came up with 73, right?
Sure.
And the microwave background came up with 67, and they're currently 5.5 sigma apart or so. The error bars are now smaller. This chart is a year or 2 old. We came up with this number. Our error bar is still large,
right?
But we have a precision measurement, and if we find more of these supernovae at this redshift, the error bar will shrink. I don't know where we'll end up.
Right, but do you have any projections about how to expect, or really not?
I think it may well stay at in the 70s. And the reason we're different from microwave background may have to do with the fact that Well, Einstein introduced his cosmological constant, right? He did that to make the universe static. This was before Hubble, the astronomer, discovered the expansion 10 years later. Then Einstein called it his greatest mistake. But it wasn't a mistake until almost 100 years later, we found out that there is actually a cosmological constant type behavior. The exponential expansion of the universe restarted a few billion years ago. And so that more generally is called not cosmological constant, but dark energy. And there's a subtle difference between the two. If it was really Einstein's lambda, it would just be a constant. Recent work by Kit Peak and the DESI, the Dark Energy Survey, has shown that the lambda value does change with time. So it's not a constant. The dark energy changes with time.
Yeah, but the phantom crossing is probably wrong, right? There's no,
What
there's
is
no
wrong?
Q. The phantom crossing, W going to less than -1, that is just, there's no quantum field theory that gives you that.
What we call the equation of state parameter, W minus 1 you're talking about?
Yes.
Yeah, it's probably not exactly -1, and it changes with time, and we don't know why that is. We have speculation, but we don't fully understand it yet. Great question. Yes? Yeah, you need a microphone? Or just speak out loud, I'll repeat it.
Okay. Given you mentioned about the infinite size of the universe for the finite size of the Big Bang,
Yeah.
what methodology do you think, if there was another Big Bang relatively close to this, how could we detect the first edge of stars coming in? So our
Well, as the... Yeah. So you're asking, given our current horizon of the universe of 13.8 billion years, if there's other universes or more of the same universe beyond that, can we observe it? Well, let's assume the laws of physics are the same everywhere, as Einstein said. So there's more universe beyond that horizon, we just can't see it. We can do two things. We can wait and then see more because we have expanded more, or of course we can't wait long enough. Or we can do physical calculations. There's maybe a third possibility. If you look at the microwave background, it contains these hot and cold patches, right? And there's a couple of cold patches that are unusually strong and cold, and the same couple of hot patches. People say, well, most of these are just formed by primeval clouds when they first formed hydrogen out of protons and electrons after the first 378,000 years. But these extremely cold patches might be because of a collision with another universe. I think that's speculation, but it's cute, and we have no way of proving it. We have no way of proving it because we got only one universe. We got the statistic of one with an error bar of 100%. Yeah, so, yeah.
To, I guess, extend a little bit on your title into cycle of life. I have some notion that James Webb also looks for biomarkers to, contribute to NASA's efforts to look for life in exoplanets. Do you have any updates on that or your thoughts on that side of James Webb's research?
Yeah, so I think, well, the periodic system, not the one in the proper proportions, but this is actually exact if you ignore the relative ratios, is the same everywhere. Right, and that's because the same star formation happens in the same kind of stellar mass distribution with the same kind of nuclear physics everywhere. So you get the same proportions everywhere. And so the building blocks of life, they're obvious from the next chart. They ain't, plutonium or neptunium or uranium. They are simply carbon, nitrogen, oxygen, silicon, iron, sulfur, and that's it, because that's the only stuff that's prevalent compared to all the others in the 103 element system. So I don't know what ETs, if they're out there, I didn't say they are, but let's say they were, what they're made of. I do know 100% sure that they better well be made out of these things. Do they have DNA? Possibly, because carbon is a lot more prevalent than silicon, and you kind of need to be in the middle of the periodic system to get a stable element to make a long change, and it's a lot harder to make that out of silicon than out of carbon. So I think other life is probably carbon-based, but I'm not that kind of specialist. I do things if ETs are out there, it's not likely that I've been there. I can get into that, but
just a quick question.
Yeah.
So you said that the lambda, the dark energy,
Yeah.
is changing with time. Is it decreasing or?
No, it's getting stronger.
It's getting stronger.
Yeah.
So is it, maybe this is not your area of expertise, but is it consistent with quintessence theories?
That I do not know. I know there's other theories. I'm a part of one team that's trying to explain it, and I must admit I don't understand this much myself. I'm an observer, not a theoretician. But these guys do heavy, relativity for breakfast and lunch and dinner, and these colleagues, they tell me that there is something in Einstein's equations that doesn't, well, it adds up, but it produces a silly prediction that if you have a singularity, a black hole rotates or not, doesn't matter. At infinity, it doesn't integrate out. The field integrals become infinite. Unless you add for every black hole a little bit of dark energy, and then the collective black, I know we need to go, the black hole growth over cosmic time that you see here would then also correspondingly increase the dark energy value. So to the extent that the universe has black holes, it produces dark energy. It's speculation. I don't know whether it's true. We need to go? Or what?
That's our last question.
Yeah, last question. Thank you all. Great questions. Oh.